Welcome to Everything STEAM. I'm your host, Sam Stanford. As a physicist and structural engineer with Jacobs Engineering, I've made many connections with some bright individuals who are either working, studying, or self-taught and passionate about our particular topics of discussion. Now that, my friend, was the sound of Are Volcano erupting in Costa Rica in 2005. And whether you think that's scary, exciting, or somewhere in between, we're here to talk about it. In this episode, my guest and I give you a two-part Volcanology 101, and then we address the ever so frustrating topic of supervolcanoes. Today, there's a lot of misinformation regarding supervolcanoes, and my guest is keen on debunking a lot of claims that surround supervolcanoes on the internet, and that does include Yellowstone National Park. So, speaking of my guest star, please meet Denali. Denali, aka Dykanite, graduated with a Bachelor's of Science in Geological Sciences at the University of Florida and is starting her PhD program in volcanology in the fall of 2023. At U of F, Denali's honors thesis was written on the subject of submarine volcanism and geochemistry, which was presented at the American Geophysical Union. And currently, she is working as a laboratory and field assistant for a volcano observatory and as a deep-sea geologic contractor. If you think volcanoes are cool or just geology in general, I highly recommend you give her content a follow on Instagram, TikTok, and YouTube at Dykanite. So, now that you've been introduced to my guest star and the topic of this podcast, we're going to head into the first segment where we're going to dive into the first part of Volcanology 101. Denali, welcome to the show. How you doing?
I'm good. How are you?
I am fantastic. I bought a couple fossils yesterday, so I'm really hyped, hoping to do some videos on that. But
Okay.
not what we're discussing today, not fossils. We're talking some pretty cool geology, but volcanology. And this first segment is all about Volcanology 101. Well, kind of. It pours into, it flows into segment 2, I guess. But we're going to start out with where are the main locations of volcanoes. So
you're going to find volcanoes at pretty much 3 main locations. That's going to be subduction zones, divergent boundaries, and hotspot volcanoes. An example of a subduction zone volcanism is going to be like the West Coast volcanoes, so like Rainier. Divergent boundary volcanism is actually what I studied for my undergraduate thesis, and that's was at a place called the East Pacific Rise, or the EPR. And then hotspots is things like Yellowstone or Hawaiian volcanism. And subduction zones are basically like it's all about tectonic plate relationships is where the locations are. So subduction zone boundaries is kind of like what it sounds like. So you've got the 2 tectonic plates and they're converging together, and the denser one gets subducted under the less dense one. And so that's a subduction zone. And then divergent boundaries also kind of sounds like what it is. You've got 2 tectonic plates and they're diverging apart. Divergent boundary. So they're diverging apart, and lava comes up between them and fills in that space, and volcanism forms all along that divergent boundary. And then a hotspot is really unique because it can happen at plate boundaries, but usually it's going to be intraplate, which means within a tectonic plate, not at the edges. And it's kind of like one of the big mysteries in geology. We don't know, we don't have it fully constrained or know for sure what causes hotspots, but essentially it's a superheated plume of material from the mantle that reaches the surface and melts everything in the crust on top of it, and volcanism forms that way. And the plume stays stationary while the plate moves alongside it. And that's how things like the Hawaiian volcanic chain form, is because volcanoes form all along that plate as we're moving over the hotspot, which is why there's multiple islands.
oh, that's pretty cool. I thought they were just like multiple different plumes, but no, it's just wow. Okay,
Yeah, it's all from the one Hawaiian plume. Yeah, isn't that cool?
that's really yeah. No, it's really cool. What's the other term where you don't see any volcanism? It just like the plume kind of stops before it surfaces. What is that called? Is it a pluton or something?
Well, yeah, a pluton is when there's something makes it superheated, but it doesn't erupt at the surface.
Yeah.
So, yeah, it cools at depth, basically.
An igneous pluton.
Yeah. Yes.
I took geology at one point, so it's not my main thing. But I guess another really cool thing to add is that I heard like over 70%. It's easier just to say the majority of volcanoes are underwater, which you wouldn't think that, but it's true.
Yeah, a majority of them are underwater. It's called submarine volcanism, and again, that's what I did for my undergrad thesis. And it's because, like, one of the reasons why the continents are like moving, and we used to have Pangea, and they're like, well, supercontinent, now they're different continents, is because of the formation of new oceans, and that's done at these divergent boundaries. So, like in the middle of the Atlantic, you have the Mid-Atlantic Ridge. That's a mid-ocean ridge. That's a divergent boundary, and it runs. If you've looked at maps of like with ridges on it, or of the Mid-Atlantic Ridge, you can see it goes all the way through. There's volcanism all along that entire thing because it's the edge of a plate along the entire thing, and it's literally making an opening in the crust to let mantle material out. So there's going to be volcanism all along that whole thing. Pretty much the entire ocean floor is all made, with some exceptions, of mid-ocean ridge basalt, which is a volcanic rock that forms the whole ocean floor.
That's pretty cool. If I recall my meeting with groovy geologist Kate, I'm pretty sure we talked about the theory of plate tectonics and the fact that they finally proved plate tectonics as a theory by studying the mid-ocean ridges and the flipping of the magnetization of the basalts, right?
Yeah. So basalt records basically like the signature of Earth's magnetic field when it forms, and you can, if you look at the magnetic field and the way it switches through time, you can look at that in the basalt. And that's one of the things that they use to finally agree on the fact that plate tectonics is a thing, which is, it's kind of insane how recent that was. Like my advisor in undergrad, they weren't teaching that when he was in college for geology. It was considered like kind of controversial.
That's pretty crazy.
Yeah.
Also, I know this is maybe a little off topic, but not really. We use igneous rock, right, to figure out how the magnetic pole of the Earth moves over time too, which is really fascinating. Like if you're not familiar, it's not true north as the magnetic north, but it's like, I don't remember how many degrees off it is, but I think currently right now it's in Canada, but it's moving towards Siberia is my understanding. Yeah,
that sounds familiar. Yeah, that's super cool.
Most definitely. I think dating rocks is fun. Dating rocks is the easiest type of dating you can do. Okay.
Yeah, that's true.
And that's a pop culture reference, not a science reference. So you briefly talked about how the three types of volcanoes come to fruition, or do you want to dive in a little bit more? Because I think it would be cool to go over like the fundamentals of like the pressures. Like, you can correct me if I'm wrong, but like it's kind of a battle between a lot of different parameters. But like if you think about lithostatic pressure versus magmastatic pressure, and then like the strength of the crust, and then whatever else is like manipulating those parameters.
Yeah, it's kind of, a lot of people think that temperature is going to be the main thing that causes melting, but that's not actually the case. There's something called decompression melting, which is where when material, for whatever reason, ends up going towards the surface, the fact that the pressure is lowering is what actually causes the melting, even though in theory the temperature would be going down because you're not as deep within the Earth. That release of pressure causes it to move past its melting point. And we use, it's hard to describe without looking at the diagram, but we use tertiary diagrams that have like depth on one side and pressure on another side and temperature on another side. And it's basically like a pull between all these different parameters, and different combinations of all of them can either have them in the solid phase or the melting phase.
Interesting.
Yeah. So like in the case of mantle plumes, temperature is the primary driver, right? Because it's superheated. But in the case of subduction zone volcanism, actually the main thing that pushes it past its melting point is the introduction of like water, like hydrous melting. Because a lot of the times the denser plate is an oceanic plate. So an oceanic plate is getting pushed under a regular plate, and the introduction of water into the system pushes it past its melting point.
There's other things that I was kind of looking into that I guess manipulate the things that you're saying. So, and again, please for people who are watching or listening to this, correlation does not equal causation unless there are evidence. Okay, so what I'm going to say is a correlation, but does not mean that it's actually, a big driver.
Okay.
You're familiar with the Milankovitch cycles, correct?
Yes.
Of the Earth? Yeah.
Yep.
So the orbit, like the change in the Earth's orbit, between elliptical, perihelion, aphelion.
Mhm.
Also, the precession of the Earth and its tilt, right? I'm curious if I'm sure it has some degree of influence, but I don't know how much, and that's kind of like hard to tell. Need a
Yeah.
lot more evidence. But my thought process is, the closer you get to the sun, the more, gravitational effects that it feels. It's almost like squeezing the
Yeah.
Earth. If the Earth's being squeezed or maybe not squeezed as much, right? You're not feeling as much pressure in the system. If that affects the amount of volcanic activity that we would see over time.
Yeah, well, I know it's an active area of research. I don't know the details of that research because that's not my area, but that is an active area of research because even minor changes in climate or like basically anything that happens on the Earth is going to affect the geochemistry, and that is my thing, geochemistry. Even minor changes in geochemistry affect the frequency of volcanism and how volcanism operates, right? So even minor changes in that are probably going to affect volcanism on a
Oh, yeah. I guess that makes sense because the lithostatic pressure would change based on glacial melt, right? You don't have as much glacier on land, putting as much pressure down on, say, and I don't want to get this wrong, but like the pressure changes, right? Between the way, the sea level increases or decreases and how much pressure you have on land versus how much pressure you have on like mid-ocean ridges.
Yeah, exactly. So a lot of the times volcanoes, that is something that they have done a great deal of research on. And that's why a lot of people are worried about the connection between climate change and volcanism, right? Is because of the glaciers. If you look at evidence of frequency of volcanic eruptions during ice ages versus other time periods, there are significantly fewer volcanic eruptions during ice ages. And it's not just because it's cold, it's because the pressure of the glaciers makes it harder to erupt. There's denser cap, I guess, on it's harder for it to erupt. Whereas if that's not there, then it doesn't take, it's not like you could just like start a volcanic eruption. It's not necessarily as though the glaciers are going to go away and every volcano on Earth is going to start erupting. They might say that's what happens in Hollywood, but that's not actually what's going to happen. But there is an established link between a warming climate and an increase in volcanic frequency. It has to be on a huge scale, like it has to literally be like ice age versus the tropics. But if global warming were to happen globally across that entire scale and we were to lose all of our glaciers, we would start seeing a higher frequency of volcanic eruptions.
There you have it.
Yeah.
So there's a couple other things that maybe, I don't know if you were planning on touching on this in segment 2, but there's 2 other things that I learned about, and that is unloading and erosion that have high influence on lithostatic pressure, right?
Yeah.
The unloading meaning like a large landslide, and then erosion, of course, thousands, billions of years of the crust eroding in a certain spot where there might be volcanic activity going on, and then it kind of like helps with the pressure release.
Yeah, well, and I mean, it all comes down to, basically, it's all just like, if there's a lot of pressure in a system, the pressure is going to try and find its way out through the path of least resistance, right? So if there's an area where it's easier for that to happen, or there's less pressure, or there's just simply less dirt and rock there, it's going to go out that way. I was going to talk about it later with the Mount St. Helens eruption, but like the reason the Mount St. Helens eruption erupted laterally out the side, which they were not expecting, is because a landslide had happened there, and there was a landslide scar. So that was now the point of least resistance for it to erupt out of, as opposed to shooting straight up like they were expecting.
Was that like the first instance that they seen something like that, where it blew out this like a side face blowout compared to like?
They didn't really know that that could happen. It's one of those things where it's like, that there's no reason for it not to happen necessarily, but you've just never seen it happen. we haven't been around that long, and volcanoes have been around a really long time. Most of the volcanic research that we have is not on volcanoes that we have seen erupt in our lifetime. It's on volcanoes that erupted thousands to millions of years ago. And there's only so much you can learn without seeing it in person. So that's one thing that is really important about the ability to do like computer simulations and stuff now, is you can input into the computer, you know, all the scenarios, all the pressure conditions, all the temperature, you know, all that you can input in there with coding. You know, you can input in there basically like, oh, let's put a landslide in there and see how this affects the model, and then play the model. And then you can, you know, say, oh, this is theoretically possible. You couldn't do that back then. That wasn't a thing. Before technology advanced to that degree, we only knew things that were possible because we'd seen it. And we hadn't seen that much because we haven't been around that long compared to volcanoes. Yeah.
That's true. And we can make pretty decent guesses based on the geologic timeline and stuff like that, and dating methods. But again, it's so weird. I have to like remind myself and also other people that science has only been around for like 400 years, like established, like the scientific like methodology. So
Yeah, the scientific methodology, the way that we think of science, has only been around that long. I will say that a lot of information we have on early volcanic eruptions in places like Hawaii and like the Aleutian Islands in Alaska, a lot of our information on those early eruptions are all from indigenous oral histories. So they're not necessarily recorded in the way that we think of as science, but it's still valuable, you know, information for learning how the world works.
Yeah, 100%. So we've talked about how volcanoes do their thing, but we haven't touched upon what comes out of volcanoes. So I think there's 4 main things that come out of volcanoes, and add or subtract if you want.
Yeah. So
gases,
yes,
ash,
yes,
lava, and volcanic bombs.
Yes. Well, I mean, you can actually, it depends on how specific you want to get, because you can actually list way more than 4 things.
Okay.
The main 4 that I usually talk about is lava, pyroclastic flow, lahars, and ash. Volcanic bombs obviously also count, and gases also. So it depends on how specific you want to get. A lot of that can be categorized under what we call ejecta, volcanic ejecta. Stuff is get ejected out of a volcano. Right? So the gases are obviously an issue, but they're a bigger issue long-term wise because of their effect on climate. And if you're standing like on the crater, that's going to be the biggest issue. The farther away you are from the site of the eruption, the less of a problem like the gas is going to be. So if you're not right near the eruption, it's not going to be as big of an issue. It tends to be more of an issue for people doing volcanic field work on things that are actively erupting or active volcanoes, because we do have to wear gas masks and such, and like carry gas monitors.
Okay.
Yeah. Lava is the one that gets the most attention in Hollywood. However, it's actually the easiest to not die from because it moves really slow. I don't know if you've ever seen lava or watched videos of lava or any of that, but it's not liquidy like people. It's like thick like syrup. Sometimes if it's really, really thick, it's going to be like thick like a milkshake. And the terms that we use to describe like the texture, the viscosity of lava is explosive versus effusive type lava. Effusive type lava tends to be a lot thinner, and explosive type lava tends to be a lot thicker and more silica rich. If there's more silica, then it's going to be thicker, and that means it's going to be more likely to explode because it's like building up a lot more pressure, and then it explodes out the top of the volcano.
And that makes sense to why the way that they're shaped.
Yeah,
right?
Exactly. Yeah, because the thickness is going to decide if it piles up around the vent or if it does that long sloping thing.
Yes.
Very scientific term, long sloping thing. But yeah, exactly. And that's what like the West Coast volcanoes, those are explosive volcanoes. The Hawaiian volcanoes, those are effusive volcanoes. But so lava is definitely the coolest in my opinion, but it's actually like I said, the easiest one to not die from. Ash is going to be the one that is the most widespread because it's going to get carried by the wind, right? So it's actually ash. Volcanic ash isn't anything like wood or ash from a fire. It's actually like tiny fragments of rock. Like So not only does it cause respiratory problems, because it's not really fun to breathe in rocks, as you can imagine, or fragments of volcanic glass in there, and you don't want to breathe that in either. But the one of the main ways that ash kills people is not actually breathing it in; it's roof collapses. Because you've probably heard of roofs collapsing from like heavy snow. If there's a lot of snow and then rain and it's heavy, wet snow, imagine a foot of rocks on your roof and then it rains. And like, that's usually what happens is people stay inside, which is, to be quite frank, if you're stuck in place, we do want you inside because it's not good to breathe that stuff in. But people stay inside because they don't want to breathe in the rocks in the air.
Yeah.
But then since they're staying inside, they're in there when the roof collapses on top of them, if there's that much ash, like right near a volcanic center. And so a lot of people die because of that.
Oh, man. So good tip for anybody out there that lives in a volcanic zone. Make sure you have a basement.
Yeah.
Yeah.
Honestly.
Yeah. Or structural engineers out there, don't design for snow, design for ash.
Yes.
I don't think we have codes for that, but we probably should. They
should make some. They might in the PNW, for all I know. They might. They're very aware of their volcanoes over there. A lot of those guys are still active. So.
Yeah, that's fair. So you name dropped lahars. Do you want to explain that?
So lahars are basically a volcanic mudslide, and that happens when water mixes with the volcanic debris, like that we talked about. So ash, volcanic bombs. There's also something called pyroclastic flow. But all of that, if it mixes with water, either if there's like a storm shortly after the eruption, or if there's a lot of glaciers on top of the volcano and it does still erupt, then all that debris mixes with water. And instead of being like slow moving or still debris, it all of a sudden has all this power behind all this water on it. And it can sometimes move over 100 miles an hour down valleys. Wow. And it's thick. It's like concrete. Like it's not like a regular mud. It's like concrete. And in some areas like near Rainier, where Rainier has had big lahars in the past, because Rainier has a ton of glaciers, the lahars Rainier has had in the past in some valleys has been as much as 500 feet deep. Wow. And that's why Rainier is monitored to an absolutely insane degree, because there's a lot of population centers right near it. The same kind of hazards can happen at a lot of Alaskan volcanoes, but a lot of those areas are really remote. And if there are populations, they're far enough away that it wouldn't be a huge thing. The main concern up here, like in Alaska where I am, is usually tsunamis, because if there's a lot of volcanic debris that goes into the water on the edge of the island, then it can cause tsunamis across Cook Inlet. So the problem is usually going to be tsunamis, not the actual debris. But that is not the case in the Pacific Northwest, where all these volcanoes and that are active with a lot of glaciers on them are. That's the main concern, is going to be lahars, because it's going to go down all the valleys, many of which have huge populations, like thousands of people.
Wow. I think this is accurate, but the United States is kind of in a really bad zone. Right. Well, I guess if you counted, like, obviously Alaska and Hawaii, like, plus like whatever's going on the West Coast, we're pretty filthy rich in terms of volcanoes.
We've got quite the collection.
Yeah.
And we have a lot of like varying kinds of volcanoes, which is interesting.
Yeah, that's nice.
Yeah.
So
nice as long as you don't live next to them.
Yeah, that's very true. So the pyroclastic flow can also be up to 100 miles an hour, and the lahars?
Yeah, pyroclastic flow can also be up to 100 miles an hour. It's going to affect a similar area in that it pretty much everything except for ash tends to go downhill, right? Yeah.
Makes sense.
But pyroclastic flow, it's like ash and like other rock fragments. The volcanic bombs are often part of pyroclastic flow, and it's over 1,500 degrees Fahrenheit usually.
Jeez.
So it moves downhill at 100 miles an hour, 1,500 degrees Fahrenheit, and just like obliterates everything, basically sets everything on fire.
Yeah, and that's funny that Hollywood was so worried about lava.
I know.
That's crazy.
There have been some good depictions of pyroclastic flow in movies. There's never been, I haven't seen any good depictions of lahars really, which is ironic because lahars kill a lot more people than a lot of the other volcanic hazards.
Yeah, I could see that. That's insane. Oh, one quick thing to note is that people don't really understand viscosity very well. But I don't remember the types of flows for lava again. You said there was two different types of flows that came out?
There's like explosive or effusive. Is that what?
Yeah, explosive or effusive. Yeah. So the
Yeah.
explosive being more viscous than the effusive.
Yeah.
So if it's effusive, it's more likely to flow like water compared to like if it's explosive, there's more resistance to it. It doesn't move as move as fast is the best way to put it.
Yeah, it doesn't move as fast. And the main comparison I always use is effusive lava is more like a syrup type texture, and explosive lava is going to be more thick like a milkshake or Play-Doh.
Makes sense. Nice. Yeah. Okay, so I think we're going to stop really quick here, take a break, and then when we come back, we're going to talk more about some case studies and then also why we study volcanism. So stick around. All right, we're back. This is segment 2, and we switched some things around a little bit. We're going to talk about why we study volcanism. Well, I don't, but why Denali studies volcanism, and I guess as a society, we study volcanism. And then we're going to get into some case studies. But before we get into that, I want to ask you a question, Denali. So what is the tallest mountain on Earth?
I think I know. I think I know what people think it is, and I think I know what it's supposed to be. I have a lot of opinions on that question, actually.
Oh yeah, the Denali and Denali, right? The Alaska reference.
Are you talking about how high of an altitude it reaches, or are you talking about the height from base to peak? Because there is a difference.
Yeah, a definite difference. We could probably both agree that it's Everest whenever it's not like base to peak, right? Yeah. It's definitely Denali when it's base to peak.
Denali wins. From over Everest from base to peak.
Well, it's not either of those or Kilimanjaro. It's actually a mountain in Ecuador, Mount Chimborazo. I
did not know that, actually.
Yeah.
I'm going to bring that up whenever people say it's Everest now.
Yeah, it's actually, so it's actually because of the shape of the Earth, right? Ecuador is in the equatorial bulge of our ellipsoid flat earthers, ellipsoid Earth. And because it's at the bulge, it's just higher, it's further away from the center point
from like
our ellipsoid.
From like center of the Earth to peak.
Yes.
That's interesting. That's a much better way to do it, I think. That's very cool.
Yeah. I don't know. I don't like the whole sea level thing. It definitely should be from the center point of our Earth.
Yeah, I don't like the whole sea level thing either.
Sea levels change, okay?
Yeah, exactly.
Yeah. Again, climate deniers.
Yeah, exactly. I'm glad we agree on that.
Okay, so cool. That was the only thing I could supply to this entire podcast. I'm happy that I could do that.
That was great.
Awesome. So let's start out with the personal question here. Why do you study volcanology?
I used to be pre-med. I study volcanology. I used to be pre-med, and for reasons
that's a change.
Both my parents are medical, and so I kind of I just went into that. I didn't really consider doing something else. I was just going to do what I was supposed to do, and that was going to be medicine. For reasons that I won't get into, I absolutely hated it. It was like killing my soul, and I quit and I dropped out. And I was like, I'm not doing this, and I'm not going back to school until I know what I want to do. And I grew up on a pretty remote island in Southeast Alaska. So I knew I loved the ocean, and I knew I loved, like, being in nature and all that stuff. And I was like, I don't know what I like for sure, but I know that I hate medicine. So I'm just gonna see how this goes. And I signed up I didn't want to go all in just on a new major on a whim, because school is very expensive.
Yeah.
So I took an earth science class and an oceanography class. So I was like, I like rocks and I like the ocean. There we go. Earth science and an oceanography class. And I loved it. I was obsessed with it. I was like, it's not even work. I don't even and that's not me saying it's easy, because it actually is very, very difficult. Like, for example, one of the reasons why I decided that it wasn't worth doing pre-med was because I had to take calculus with analytic geometry. Guess what I had to take as a geology major? Calculus with analytic geometry. And that was what
there
I
you
was.
go. There you go.
Yeah, exactly. So I had to take it anyway. So I ended up having to take a lot of the same classes I would have if I had stayed in pre-med, but it was worth it now because I liked what I was studying. But anyway, in my oceanography class, I remember reading about mid-ocean ridges and reading about seafloor spreading and divergent boundaries. And because, like most people in the US, I did not get a very extensive earth science education in high school because it's not included in a lot of curriculums. I had no idea that the ocean floor was formed because of ridges. I had no idea there were underwater volcanoes. I didn't know any of that. And I remember reading it and being like, this is the coolest thing I've ever. What do you mean there's underwater volcanoes? What do you mean the entire ocean floor is pretty much the same thing? What do you mean that there's new oceans being formed and that's what's moving the continents? There's a new ocean being formed at the East African Rift right now, a brand new ocean. I was like, that's the coolest thing I've ever heard in my whole life. I want to do that. And then that's what I did my undergraduate thesis on. Is after those two classes, I found University of Florida, which is where I went to school, and I was able to get on undergraduate research with an advisor who has spent his entire career studying submarine volcanoes. And so that's what I did my undergrad thesis on, was do my research under him as I saw it. And I was like, I want to do that. And then I went and did it.
That's pretty cool. Do you get to do any diving?
Not as part of that thesis. Those things are like they're way too deep to just like scuba dive to do it. They were collected via a deep sea, like an ROV, remotely operated vehicle, like an underwater robot basically, that goes down and gets the rocks. So that's how I have scuba dived many times, but not to get rock samples. Because
you don't want to be like that dude. What is his name? James Cameron or whatever, that like goes to the bottom of the ocean. Do you want to be like him?
I would love to do that. My advisor is like that guy. He goes down in something called the Alvin, which is a human operated, an HOV, a human operated vehicle that goes down and collects rocks that way. But not yet. One day, but not yet. I haven't done it yet. I just got the rocks. But submarine volcanism expanded to regular volcanism because I saw lava.
Just a random factoid for people that are listening or watching. When you come back up from the ocean floor, you have to do it extremely slow so that you don't go up too fast and literally explode yourself. So it takes a long time for you to leave the ocean if you're going pretty deep. Just saying. There's levels to it. I don't know the levels, but I just know if you come up too fast, you're going to pop.
Yeah, if you come up too fast, you can get very, very sick. A majority of the time, diving is not actually spent at the bottom. It's spent, going down and coming up at a safe enough speed that you don't get nitrogen blood poisoning.
Yikes. Hey, there it is. Perfect. So why, as a society, why, like a scientific community, why do we care about studying volcanism?
Well, I mean, the most obvious answer is that a lot of people die from volcanoes. That would, people, whenever I make volcano educational videos, people are like, I don't understand why people even live next to volcanoes. But there's a lot more active volcanoes than people think. A lot of people that I've talked to think that all the ones on the West Coast, except for like Rainier and St. Helens, are dormant. But no, a lot of those guys are active. They haven't erupted, recently, but they're still active. Like over 800 million people live within 100 kilometers of an active volcano. I think that's like 62 miles. Something. I can remember the conversion factor, but within 100 kilometers of an active volcano. And if you're that close to a volcano and you're there during a volcanic eruption, that means you're going to be subject to all of those very deadly hazards that we talked about earlier. And then also, just aside from the human life aspect, there's the economic aspect. Even if it was just lava flow and a human could get out of the way, you can't move a building. It's still, it can cost billions of dollars in damage to infrastructure. And then not to mention like agriculture, like the largest death toll from a volcanic eruption was Mount Tambora, which is like in 1815, I think, and had an estimated death toll of like 11,000 from like immediate hazards, which is like pyroclastic flow. But the long-term death toll is thought to be over 100,000. Because there were so many food shortages following the eruption. So not only because the ash like destroyed crops by landing on it, but also if it's a huge eruption or if there's multiple eruptions in a short period of time, it causes a volcanic winter where the global temperature drops for a short, period of time, or sometimes not a short period of time, depending on the size of the eruption, which messes up everybody's agriculture. So people starve to death because of this stuff, like long term. Yeah. So, and then also airspace, like the flights going over volcanoes. That's the main reason why the volcanoes in Alaska are so heavily monitored, even though a lot of them are remote, right? But hundreds of flights go over the Aleutian volcanic chain every day. And can you imagine people who are afraid of flying, finding out that they're flying directly over an active volcano?
Yeah.
So that's the main alerts that the Alaska Volcano Observatory is putting out is flight alerts, so that people know if it's safe to fly over. There was actually an instance in 1989, the Redoubt eruption in Alaska, where a flight flew through the ash cloud. They thought it was just like a regular, I don't know what they thought, but they flew through it. Maybe they thought it was just a dark cloud. I have no idea, but they flew through it. And what essentially happened is, since it's not just regular ash, since it's rock fragments, going into the engine, it was superheated and became volcanic glass and coated the entire engine in a layer of volcanic glass. And the plane like fell out of the sky and dropped like a couple miles. They were able to get it started eventually, and nobody died.
Oh, that's
but
good.
still, can you? That's
crazy.
kind of a big deal. And if you have hundreds of flights flying over these volcanic systems every day, there's a lot of opportunity for things to happen. And so that's why they have to be monitored, and that's why we have to understand what causes them to help predict eruptions and prevent catastrophes like that from happening. And also just it's cool, but you can't get you get more funding by saying the other reasons, not just like, it's cool, I want to know.
True. Yeah. So we made volcanoes out to be like bad, like it feels like, or dangerous or scary. So maybe you could elaborate on why volcanoes are good for society, why you should be happy that they exist.
Well, the number one reason is that's how we get rocks.
Yeah.
and the entire Earth. Like, where do people think the crust came from? The Earth used to be a magma ocean.
Yeah.
It's just like an ocean of lava, and eventually that had to cool and become rock, and we have the crust. But that's how you get land. And if we didn't have land, we would all be dead because we would have melted into the mantle. Like we require that to live on Earth. So that's the first thing. But the other thing is primarily agriculture. All of the most fertile areas are due to volcanic soil and due to the chemistry and everything, all the nutrients that's provided by eruptions. So that's another reason why people still live in heavily volcanic areas, is the same thing that makes it so dangerous to live there, because it could destroy their crops, is also the main reason why their crops do so well. And then also there are some species of animals that only live around volcanic regions or active volcanic regions because of the heat associated with volcanic regions. Like, there are species of birds that only lay their eggs on active volcanic soil because it incubates the eggs for them.
Nice.
Yeah.
That's really cool.
Yeah.
Yeah. And, that time period whenever, the Earth was just covered in magma or lava, I guess it would be lava in that instance, right? That was the Hadean, and volcanic eruptions put stuff into the atmosphere. A lot of that stuff was oxygen gas.
Yep.
And because of where the Earth formed, which is, closer in the protoplanetary disk, we have a lot more, I would say, iron, oxygen, silica, but we don't have a lot of hydrogen. Where that hydrogen came from and how we have water is because hydrogen came from the sun, bombarded the atmosphere, fused with oxygen, and fell out of the sky eventually as water. And that's how most of the water that you have today on Earth came from the Hadean, which is pretty cool.
Yeah, that is very cool.
Yeah. So thank volcanoes.
Yes, exactly. I agree.
Drink up.
We need that.
Yeah. That's pretty cool. So I've seen your images and stuff. You've been near volcanoes, and you've seen some lava flow up close. Tell us about it. Tell me about it, and also them. Yeah.
Yeah, so that was my first like volcanic fieldwork experience that I got to do my senior year when I was at University of Florida. And the same advisor who I did my undergraduate thesis research work, I heard about the Iceland eruption, and it was like 2 a.m. and I like emailed him and I was like, I have to go. Like, can you help me? And he was like, yeah. And he got me in touch with someone from the University of Iceland who he had met at a conference like a decade earlier, and asked if I could do field work with them. And so I ended up going and doing field work at the Fagradalsfjall eruption in Iceland, the first one. And it was like life changing. I was like, I'm never doing anything else. I'm obsessed. Because it's you would think that we're able to do that kind of stuff all the time, but even volcanologists, a lot of the time, if you're studying explosive volcanoes, you are not going to want to go there when it's erupting because it's exploding everywhere.
Right.
And it's yeah, and so it's very, very dangerous. And so a lot of the times you're not going to want to be there when it's actively erupting. And the Iceland volcanoes, this one at least, is primarily an effusive volcano, so it's not explosive. It's just the long, beautiful lava flows. The gases are an issue. So during some moments when I was doing field work, I did have to wear a gas mask. But even though it's still dangerous, there's not explosions everywhere. So you can visit it more safely, which is why it ended up becoming a tourist destination. You probably remember all those videos of, everyone hanging out around the volcano. But so that's why I was able to visit that one. And it was definitely a, hopefully not once in a lifetime experience because I'm doing this for a job now, but even among volcanologists, it is very, very unique to be able to see something like that up close.
Sweet. That's really cool.
Awesome.
How was Iceland? Did you get to go into Reykjavik?
Yeah, I did. I got to do a couple of touristy things. Most of the time I was camped out on the volcano, but I did get to do a couple of the other things, and it was beautiful. I'd love to go back and see more of it. I love Iceland. Pretty much a good 2/3 of the projects I applied for grad school are all Icelandic volcanism projects. So
sweet.
One of them is literally a project on Fagradalsfjall, and during my meeting with the advisor for it, I was like, I already have it tattooed on my arm.
That's dedication.
I'm ahead of the game.
Nice. Yes, there's commitment. There's reasons to get topology as a tattoo. Honestly, it's a really cool tattoo.
Thank you.
Yes. Curious. Another, I guess, personal question before we jump into case studies.
Mm-hmm.
What is your favorite volcano and why?
Well, see, my favorite, it's not that interesting of an answer because my favorite volcano is the one I have tattooed on my arm. Yeah, I'm sorry. That is my favorite. It's the one that's closest to my heart because it was the first real volcanic experience that I had. But my favorite volcanic system is going to be the East Pacific Rise because that was what my undergraduate thesis work was on. And mid-ocean ridge volcanism was the first thing that made me fall in love with geology. So.
Yeah, not Mount Fuji.
No, sorry.
Sad.
Is yours Mount Fuji?
What's that?
Do you have a favorite volcano?
I think it would be Mount Fuji. It's gorgeous.
It is very beautiful.
What you think of a volcano? Well, at least for the layperson like me.
Yeah. If you're a volcanologist, you probably think of the one you spend all day studying. But for regular people, I imagine that would be one that they think of.
Yes, exactly. So we wanted to talk about case studies. Do you want to take us through a couple of them?
Yeah. So one of the things we already talked about earlier, so I won't go super into it, but of course it is the Mount St. Helens eruption. And it was kind of just what I was saying earlier, which is that we haven't been around all that long compared to volcanoes. A lot of these people are like, why do volcanoes never erupt? Why are they never erupting? It's actually they're erupting, quote unquote, all the time for volcanoes because they work on systems that go off of every, maybe they go off every couple of 1,000 years, and we don't live that long. So it's not that they're never erupting. It's just that they operate on a different time scale. We live such relatively short lives compared to volcanic systems that even if it's a volcano that is considered one that erupts frequently might be every 500 years because other ones haven't erupted in 1,000,000 years. It's that kind of thing. But a lot of the knowledge that we have from studying volcanic eruptions until technology came on the scene was from things we could directly witness, because we can look at the rocks and we can look at the formations, we can look at the geochemistry, and that can tell us a lot about the volcanic system. But it's hard to predict things like the Mount St. Helens eruptions where it shoots out the side if you've never seen that before, right?
Mm-hmm.
So that's one of the reasons why it was so much deadlier than expected, because when it erupted up, instead of when it erupted to the side, it went a lot farther. Whereas if it erupts upward, it'll fall kind of, around the edges and won't have quite as much force. But there's actually a lot of volcanic eruptions that behaved in kind of like unique ways, and that kind of helps us. That kind of helps us gain a lot more knowledge and be able to predict these weird things that might happen. Iceland is a good example because Iceland is not only a hotspot system, like the entirety of Iceland is above a hotspot.
Okay.
It's also right on the mid-Atlantic ridge. So that's a really, really unique environment because it's not just one kind of volcanism. It has mid-ocean ridge volcanism and hotspot volcanism.
Okay.
Which makes it way more complicated to study, but it also makes it very, very cool. And then there was another eruption in Alaska, which is the Katmai and the Nova Erupta eruption. And basically what happened is Nova Erupta was an eruption from a new location adjacent to an existing volcano, which is Mount Katmai, but it sourced its magma from the same reservoir, which is not super common. But it sourced its magma from the same reservoir, and the Nova Erupta eruption wasn't that big, but it drained all of the magma from underneath Mount Katmai. And so basically this area of the crust beneath this giant volcano was like hollow, right? And so Mount Katmai, the caldera collapsed, the peak collapsed and released more ash. I think it had more ash than any other eruption in the 20th century, like more than Krakatoa. More than any other one in the 20th century. And it wasn't even Katmai that was erupting. There was a little eruption over here and it stole all of its magma, but then the collapse released so much ejecta into the air. And you can find that on like other continents, ash from that eruption.
That'd be like a whoopee cushion almost.
Yeah.
Dang. You need to I think volcanologists need to come up with like a standardization for like these and then name that one the whoopee cushion volcanic event.
I'll bring it up at the next conference.
but legit, is there an effort to create some sort of a standardization so that you can pull similar characteristics and be able to, I don't know, cross-reference different volcanoes and make better predictions? Or is it more like a case-by-case study?
It's a little of both. There are a lot of systems, but volcanic systems themselves are so complex. I'm not aware of a single comprehensive system that addresses everything, because everything is kind of interconnected. Like there's the volcanic explosivity index. Anything that is going to be called a supervolcano has to have like a certain level on the volcanic explosivity index. I usually hear that it's supposed to be at an 8, but I've also heard some that are on a 7 that have been called supervolcanoes, and I'm not sure if that's now part of the official terminology or if news outlets are just making stuff up. Not really sure which it is. But that's one system that we have. But then we also we categorize things explosive versus effusive. We categorize things subduction volcanism versus hot. We have all kinds of different ways to categorize these things. But they're not necessarily going to be all encompassing for every aspect, because even though in general, for example, it's a rule that effusive volcanoes or volcanoes with effusive type magma with less silica, right, do not have explosive eruptions. Hawaiian volcanoes have had explosive eruptions. And the reason that they have explosive eruptions is because it's not a regular explosive eruption like they have in the Cascades on the West Coast. It's what's called a phreatomagmatic eruption or a phreatic eruption. And basically, what happens is both Kilauea and Mauna Loa have done this in the past, but they alternate between effusive and explosive. And the effusive eruptions happen when the magma level is high, and then obviously it erupts out the top because the magma level is high. But then when the magma level gets low enough that it's close to the water table, the water can get into the reservoir where the magma is, which creates steam when the water hits the magma. And then the steam builds up pressure within the system and causes an explosion.
Ooh.
Yeah. So yeah, it is. That's actually that's an area that still needs to have a lot more research, is phreatic eruptions. Lots of people are working on it, but they are by far the least predictable kinds of eruptions. That is the kind of eruption that the White Island eruption that was in the news all the time was. Because even if you're monitoring a volcano, a majority of catastrophic eruptions, you're going to be able to see precursors if it's well monitored for years to decades before it erupts. But it is extremely, extremely difficult to predict all the myriad of ways that water could somehow make its way into a reservoir. So those are by far the least predictable kinds of eruptions. It's going to be a phreatic or a steam eruption.
Well, that's really interesting. I think we're going to take a quick break, and then when we come back, we're going to talk about, well, the title's long, but it's all about misinformation, supervolcanoes, and debunking and discussing these things, because it is actually really important, and there's a lot of misinformation out there. So stick around. All right, we're back. This is the final segment. Thanks for sticking around. It's been a really fun episode. Some jokes, some dangerous conversation. It's been fun. It's been a good time. So this last segment, we're going to be talking about supervolcanoes and misinformation. It's been quite a struggle for Denali, not for me, but in that department. Yeah, so we want to start this out with talking about, actually, maybe I want to pose the question first before we do anything. Should we be worried about supervolcanoes, and then why or why not? I'm curious.
So on a large scale, the simple answer is no. But it's a more complicated question than you think, because you should always be overly cautious around any active volcanic system, and any supervolcanic system that is still technically active. People tend to approach it as like, if a scientist is saying, oh, you don't really need to worry about this that much, people take that as meaning that it's absolutely, definitely 100% certainty, never going to erupt again, we can stop monitoring it. And that's not what we mean when we say we don't need to worry about it. We just mean that the odds are obnoxiously low, and that a lot of the information that people hear about these volcanic systems is either outright a lie or just vastly over exaggerated. A lot of money has been invested into research on volcanic systems, but that doesn't mean that like science is not infallible. It's constantly changing, and volcanic systems in particular, because it's not like a volcanic system is just enclosed. The true volcanic system is really the entire Earth, right? Because it gets its source from the mantle, and there's mantle convection. It's literally the whole planet is the volcanic system. So even though we're researching it a lot, it's always something that can be expanded on, and there's always like a chance of error, as with anything in science. But that doesn't mean that a supervolcanic eruption is an imminent threat, and it doesn't mean that you should stay up at night, worrying about it. We would, for any catastrophic large-size eruptions, you would have weeks to years to potentially decades worth of activity signaling that it would do that. And now, like I said earlier, small phreatic eruptions, those can have relatively minimal time beforehand. But a supervolcanic eruption is not a small phreatic eruption. That is not something that can happen from just, a small amount of water getting into a magma reservoir. These are huge, catastrophic, horrible, not the biggest eruptions in the world, because those are actually flood basalts, but one of the biggest types of eruptions in the world. And so if you're an avid hiker or a science buff, and you literally want to go visit an active volcanic crater, yes, you should always technically be prepared for the possibility that something happens. But it's not to the kind of thing where people need to be staying up at night worrying about it. You don't need to avoid necessarily, you don't need to avoid moving to volcanic regions any more than you need to avoid moving to other regions. Like, the living and working and existing in the presence of volcanoes is a risk. But like in the last 500 years, roughly like 270,000 people have died as a result of volcanic eruptions. Guess how many have died of hurricanes in that same time period? Over 500,000. There's actually a website called volcanolive.com, and it has a ranking of things that you're more likely to die from than a volcanic eruption. Like, you're quite literally more likely to die in an elevator accident than in a volcanic eruption. Are you increasing the odds if you live right next to one? Yes, you're technically increasing the odds of dying in a volcanic eruption, but it's just like you're increasing the odds of getting hit by a car if you cross the street. If you stay aware of the risk and act accordingly before you visit a volcano or before moving to a volcanic area, it's just not as big of a risk as people like to make it out to be, where they're like, oh, it's going to erupt tomorrow. It's not going to erupt tomorrow, because we would have started seeing precursory activity like at least a couple of months ago, probably years ago, for a volcanic eruption that big. Not necessarily all eruptions, because some of them do happen with minimal warning, like I said, but for a supervolcano level eruption, there would be precursory activity. And so it's really important to discuss things realistically, and discussing things realistically means it's not as simple as necessarily saying you definitely never need to worry about it, or saying you should worry about it all the time, because the truth is very much somewhere in the middle. And there's a lot of misinformation about volcanic systems and science in general. And like I said, oftentimes it's either an outright lie or it's an exaggeration, because selling fear gets people to watch things. That's how they get people interested, is they leave out all of the information that says how either outright not true it is or how unlikely it is to happen, and they capitalize onto things that make you think an apocalypse is going to happen tomorrow, which there is no evidence of.
Cherry picking.
Yes.
Yeah.
Exactly. Yeah.
So I have just a quick question. Well, might not warrant a quick answer, but so super volcanoes, right? I mean, they're mentioned, but like, how do we know when it is a super volcano? What constitutes a super volcano with respect to the VEI, right? The volcanic eruption index. Did I get that wrong?
Volcanic explosivity index.
And
so most volcanologists hate the word supervolcano, because it implies we hate that word. It implies I think the original scientific term was super eruption. Any eruption that is on the volcanic explosivity index, like level 8, which is the highest it goes, is a super eruption. And that's based on the volume of volcanic ejecta. I don't remember the exact number of cubic kilometers that is, but it's a huge amount of explosive and ash, right? That is a super eruption. But we don't like the term supervolcano, because that implies that volcano only has super eruptions. And that's just not the case. Yellowstone has literally erupted multiple times since the last super eruption. But most of the time, the volcanic eruptions at Yellowstone are either small phreatic explosions or very relatively mild lava flows, like the kind that happen in Hawaiian volcanoes. So it's literally already erupted since the last supervolcanic eruption. And most supervolcanoes will only ever have one supervolcanic eruption. Yellowstone has had 3, but most of them will only ever have one. So the thing that makes it a supervolcano is just that it's had at least one super eruption. Technically, under the right conditions, any volcano could be a supervolcano. It just hasn't had a super eruption yet. Now, don't run wild with that, because it's not like one where it doesn't, if there's not enough magma in the reservoir, it's not going to have a super eruption. But like in theory, it's not as though this is its own separate type of volcano that has these massive explosive eruptions. It's a regular explosive type volcano that happens to have one big enough to categorize it as a super volcano or have super eruptions. But that's why we don't like that word, because people tend to act as if that's some prophetic thing that the next Yellowstone eruption is going to be a super volcano eruption. It's like, no, Yellowstone has actually had thousands of eruptions. Only 3 of them have been super volcano eruptions, and it's literally erupted since the last super volcano eruption, and it wasn't particularly impressive.
I guess they do leave that out, the fact that, there has been an eruption in between the last super eruption. Yeah, and that's the thing is, like I said, sometimes they are outright lying, but sometimes that's not quite what they're doing. Sometimes they are just exaggerating or leaving out anything that would make you feel better. Because if you feel better, then you're not going to want to panic watch the next 10 episodes about how we're all going to die tomorrow. That's fair. So you did mention that there are some things that they're precursors to the eruption that you can identify. What are those for the common person?
So the biggest thing is earthquakes. That's mostly because that's the most advanced technology. Like I said, I do geochemistry, and a lot of people are working on geochemical methods for eruption prediction, but it's not that advanced yet. The biggest way we have to to predict eruptions is to look at earthquake activity, because magma movement can cause earthquakes, but a lot of other things can also cause earthquakes. So that's usually one of the first things that they try and figure out if there's an earthquake swarm, is they're trying to figure out, is this tectonic or is this magmatic in origin? I don't do that segment of volcanology, so I don't know exactly how they figure that out, but that's usually the first thing that they try and do. And then another thing they do is they can also use seismic waves to look at the size and composition of the magma reservoir. And so with looking at seismic activity, there's there's seismic waves, and they put seismic waves through the ground and they see how they react to the kind of material they're moving through. They will move at different speeds through thick material versus more liquidy material. And they have done this at a lot of volcanoes, and they have specifically done this at Yellowstone, and they use that to see what is happening with the magma reservoir. And what they have found at Yellowstone is that while there is still magma in the reservoir, it is actually too cold and too solid to be erupted. There is not a high enough what's called a critical melt fraction. There's not a high enough critical melt fraction for an eruption to occur. And that's what they tend to do with these volcanic systems, is they want to look at not only are there earthquakes happening, but also even if there is no unusual activity happening, they still want to be researching the volcano to figure out what the situation is. And that's what they're trying to do at Yellowstone, is there's not currently thought to be enough eruptible magma in either of Yellowstone's reservoirs, because it actually has two, to sustain an eruption at the current moment. Now, obviously, eventually that could change, but if it suddenly started getting hotter and having a lot more liquid magma, that would increase activity, that would increase earthquakes, that would increase hydrothermal activity. We would see massive changes if it were gearing up for any kind of eruption, much less a super eruption.
Okay. Interesting. Yeah. So those are the main precursors. The seismic. Okay.
Yeah, and also degassing.
I was going to say gases.
If there's an increase in gas emissions, or if there's a change in the composition of gases, that's actually the main thing they're looking at to predict phreatic eruptions. What we were talking about earlier is they have noticed that before a phreatic eruption, there's a slight change in the gas content being ejected.
Cool.
Something to do with sulfur. I don't know that area of it, but
that's pretty cool. I heard on another podcast, there was a volcanologist that was talking about the sound waves that are emitted by volcanoes. Are you interested in that at all?
I don't know much about it, but I have heard things about it before, not from a podcast, but there was someone I met at a conference one time who had a website that was like the sounds of volcanoes. And it was basically, he made like music with volcanic frequencies, which is kind of cool.
So back to Yellowstone, because I know we're talking about misinformation. I just wanted to do a quick sidetrack there, just because it was on my mind. But yeah, so Yellowstone, they say the date is what, every 640,000 years? What's up with this whole, like, it's due? You want to go through that?
Yes, I absolutely want to go through that. So first of all, what people will usually say is that I think the estimate is usually it erupts every 600,000 years, and it's been 630,000 years, so it's 30,000 years overdue. I don't know where they got that number. I think somebody made it up, because if you actually look at the time distance between the major supervolcanic eruptions, it's 725,000, not 630 or 40,000. So I don't know when that got in there, but I've never read that number in any actual like legitimate research paper, and that's not the official number that's on record with the United States Geological Survey, because the United States Geological Survey puts out all kind of Yellowstone misinformation, like working against it, like correcting the record. You can literally search USGS Yellowstone misinformation. There'll be a whole page that says exactly word for word what I'm about to say and what I say on every single Yellowstone video I make. And I'm like, guys, you're not arguing with me. You're arguing with the USGS, who's been studying this for decades, but whatever. Yellowstone is not overdue. It's not overdue. That's not accurate at all. You cannot take the average of a few like eruptions and use it as a countdown to the next one. For one thing, and just in terms of scientific integrity as a whole, that is a horrible data set. Like what, 3 eruptions? That's a horrible sized data set. You can't do anything respectable with that. And then on top of it, like I said, the math doesn't work out, because if you actually look at the math, then it's more like 725,000 years between eruptions. So even if volcanoes did work that way, which they don't, they do not work on cycles, they do not work with predictable, you can't do a countdown to the next eruption. But even if they did work that way, it wouldn't be due for several thousand years. So we're not overdue at all. I know exactly where people get that idea, because there's literally a series called Super Volcano that was on the Discovery Channel in the early 2000s. And on the poster for it, it says like, it's deadly, it's overdue, super volcano. And I'm just like, but anyway, it is not overdue. That is not accurate whatsoever. And it's, I think it's just become such a, people get annoyed when I say pop culture, but it's a cultural phenomenon, basically, this obsession with Yellowstone super eruptions. And I think that's why misinformation on it is so rampant. People are so emotionally invested in this idea that their third grade teacher told them, 20 years ago, that we're all going to die in a Yellowstone eruption, that no matter who they hear it from, they're going to get upset that you're counteracting that. A lot of the information on Yellowstone, when we didn't have the technology to necessarily forecast things, it was not necessarily like, oh, we're all going to die tomorrow, but they didn't have all this information that showed that Yellowstone is not likely to erupt, like what I was talking about with the magma chamber and all that stuff. We didn't have that. All we had was evidence of past eruptions. So if you're a scientist at the beginning of geology and you're going there and you see evidence of this huge, massive eruption, the only thing you as a scientist can really say is, here are the elements of this catastrophic eruption. And then people hear that and run wild with it, because we don't have any evidence for the fact that it isn't likely to happen, because technology isn't that advanced. So it's not like that original research wasn't accurate, but it's not current. So you have to look at the evolution of science and what we have learned since then in order to get an accurate picture of it. Like, I also hear all the time that Yellowstone is going to set off the Ring of Fire.
What?
It's going to set off the Ring of Fire, which, for anyone who doesn't know what the Ring of Fire is, yes, set it off specifically. I've heard the same thing about Hawaiian volcanoes. It's going to set off the Ring of Fire, which, first of all, Yellowstone is not on the Ring of Fire. It's a completely different volcanic system, not on the Ring of Fire. Hawaii is also not on the Ring of Fire. Not related at all. But the Ring of Fire is called the Ring of Fire because it's at the edges of tectonic plates, and it's an area with so much volcanism that there have been volcanoes erupting on it continuously for millions of years. You can't set it off. It's been set off. It's been set off for a long, long time. Millions of years, in fact. So you cannot set, there were, I think, maybe there were like 52 or 54 eruptions on the Ring of Fire just last year. There's major eruptions on the Ring of Fire all the time. So no, Yellowstone is not going to set it off. First of all, even if Yellowstone were on the Ring of Fire and the Ring of Fire were not set off, there is no evidence that a volcanic eruption at one location can set off a volcanic eruption at another location, except in the instance of what I said with the Nova Erupta eruption, where they share a magma reservoir. But even in that scenario, it wasn't like it triggered another eruption. It just collapsed something because it stole all its magma, right? But if they don't share a magma reservoir, they don't have any relationship like that. They cannot trigger each other. So volcanoes cannot trigger each other. It's not on the Ring of Fire, and the Ring of Fire has already been going off for millions of years. So this idea that Yellowstone is going to set off the Ring of Fire makes absolutely no sense, but it shows up in literal articles. I'm not going to say which news outlet it was because I got them to take it down, but literally people in my comments, I got so often referred to this one article, news article, that literally said on it, Yellowstone is the most dangerous volcano on the Ring of Fire. And I was so sick of seeing that in my comments that I wrote to the website that published the article. And I was like, look, what you're saying is in direct contradiction to USGS. And they later cited USGS as a source, which I know for a fact is not where they got that. So, but a lot of the times people would say like, scientists have said, but then don't specify which scientists. So,
of course.
You know.
It's a blanket statement.
Yeah, but I literally wrote to them and I was basically like, with all due respect, here's all the reasons why you're wrong, and here's why this is irresponsible. And they were like, well, too much time has passed for us to change the article, but we'll remove it for you. And I was like, great. But so it's such an intense, it's such a big thing that the places that people go to try and fact check literally have the wrong information, because one person reports it wrong and then 10 people cite that one article and nobody actually looks at the USGS website. I have no idea why. But the same thing happened when a couple of months ago there an article put out by the Yellowstone Volcano Observatory had a new estimate on the amount of eruptible magma. I don't know if you saw anything related to that, but all the headlines were like, deadliest volcano that will destroy humanity next time it erupts has double the amount of magma in the reservoir, double the amount of magma, double the amount of, like, all. What happened was that the original estimate of the amount of eruptible magma was between 5 to 15%. The new estimate is between 16 and 20%. So are they technically lying when they say double? No, not if you decide that you're going to go with the lowest estimate on the first one and the highest estimate on the other one. But that's not actually
cherry picking.
What happened. And it's not even double the amount of magma. It's double the amount of liquid eruptible magma. And both of those numbers are still far below the critical melt fraction needed for an eruption, as very openly stated by the Yellowstone Volcano Observatory multiple times after all these articles started coming out. So it's that kind of thing. Like you said, they cherry pick and they leave out anything that could possibly make anyone feel better, because Yellowstone is such an iconic thing and they get so much traffic from it. They don't care about the real information.
Interesting. And I want to jump back just really quick, because this number thing has been in my mind, and the fact of cherry picking, and also the progression of scientific studies.
Yep.
Right. This 600,000 years versus the 725,000, that's obviously a long time. But I wonder if, there's two things that come to my mind. Like, are they cherry picking a data point that makes sense to the time frame that we're sitting in now, so they can do fear mongering tactics? Or are they looking at a study that was initially published X amount of years ago that had a level of error to it, and they cherry picked based on today's circumstances? It seems plausible in both ways. Either way is that they're wrong.
Yeah, so. I think it's a little bit of both. I do think in some situations there is an element of maybe not necessarily malice, but lack of accountability for what people are reporting. However, like I said, sometimes people are not outright lying, or they're not making things up. Sometimes they are just using outdated research.
Yeah.
And on the one hand, that's kind of understandable sometimes, but also if your whole job is to report, then why are you not reporting the most recent information from the scientific body that studies this stuff? They don't keep outdated reports just readily available on usgs.com. Like, no, they give you the current up-to-date information, and they may say, we used to think this, but now we think this. They're very careful about how they present that stuff. So while they might be using outdated research, and maybe at one time that's what we thought it was, I do think that it's either malicious or it's ignorant to be a journalist and writing things like that and choose not to look at the most recent info. Like, maybe they're not just trying to be irresponsible, but they are if they're not looking at the most up-to-date stuff. Because I feel like if you're the kind of journalist that writes about science, that does scientific communication, then you should know to always look at the most up-to-date information. Literally, things that I learned in my geology degree in my classes are now outdated. Some things, like the basic model that we base subduction zone volcanism off of, violates basic mass balance principles. But that's the best that we have, so that's what we taught, So it's when I make videos about things that I don't deal with on a day-to-day basis, I always check the most recent information. It doesn't matter if I got an A on my exam on that. It doesn't matter, because it's been a couple years since then, and new information is coming about all the time. If you're going to write about scientific content, you need to be keeping yourself up to date on the most recent research. Otherwise, it's irresponsible, in my opinion.
I couldn't have said that any better. I also kind of want to make a statement about maybe the number itself and where it comes from, because you use dating methods, radioisotopes, to get justifiable round numbers for how old, say, that rock was, meaning when it came out, the volcano, when it came out, when it solidified, and maybe they took a study that had outliers in it. You know what I'm saying? Because whenever you date radioisotopes, already there's a built amount of uncertainty in the results, because we use half-life to account for time it takes for this amount of isotope to turn into this amount. The most probabilistic answer is the half-life that we have established, but there's still outliers that don't align with the majority. That happens. It's called uncertainty. So, I mean, it could be that they were cherry picking data. I mean, that's quite possible.
Yeah.
And maybe they just didn't understand what they were looking at, and that's fair. Well, kind of. It needs to be checked, right? You
Yeah.
need to have a peer review for your paper. But the
think
best
it
way
was
to do
fair
that,
at the time, but it would not be fair to be referencing that in modern day.
yeah,
Like older data in modern day if we had something updated. But yeah.
and that it even could have been from like a study that no, I can't even say that, because like, if you're dating something that's 720,000 years ago, the level of error or uncertainty wouldn't give you 100,000 years of change.
Yeah.
That's a lot. That's a high percentage of uncertainty.
That's the thing, is if the uncertainty is like, plus or minus even like 2%, well, 2% of millions of years is a lot of years, which is another reason why in general, you can in terms of Yellowstone specifically, like most of the information I get on Yellowstone, like I don't research Yellowstone for a living. I do other volcanoes. Everything I get on Yellowstone is from USGS publications, and there's even a very good openly available pub talk by the scientist in charge at the Yellowstone Volcano Observatory. And that's something that he talks about, is this is why you shouldn't even be using numbers like that to try and predict an eruption, because the uncertainty, the percentage of error is good chance it's pretty high. And we have other things. It's a better practice to use other methods to look at the current state of the volcano and use that to decide the likelihood of an eruption, than to take these numbers that have such a high uncertainty anyway and try and use that to predict, oh, well, it's going to erupt in this many, hundreds of thousands of years. It's just not a good method of prediction. And even that's why scientists who study this stuff they don't use that for prediction. It's a good thing to know, to keep in context. Oh, here's, to get an idea of how active it is, how often it erupts. But it's not a predictability tool, and we don't use it that way in volcanology. So that's where the problem comes in, when people who do not study volcanology try and use that as a predictive tool. Because of these uncertainties that you're talking about, it just doesn't work like that.
Yeah, and it's not like, and I totally, that makes perfect sense. It's not a predictability tool, but it is something that you can use for predictions of possibly how long it could be erupting or something like that. I mean, it's like maybe another tool, but it's not something that's like.
Yeah, it's a tool, but it's not universal, and it's not a prophecy, is the main thing. It's a good thing to keep in mind, but it's not a rule. The volcano doesn't have a set, like, just because the average number of eruptions, the average length of an eruption beforehand was so many years, doesn't mean the next one is going to be that many years.
True.
But it's still a good thing to know. But a lot of the times people are looking for black and white answers when they look to scientists, but that's the problem with trying to be a scientist and be a science communicator. Science is not black and white. All of these things every rule has an exception, and that's not even reliable enough to be a rule because volcanic systems don't work that way. So it's a good tool, and it's something we need to know. That's why we date these things. Yeah. But it's one tool of many that give us the whole picture. You cannot take just that information and try and use that as if it's dictating the entire system.
Agreed. And I want to say one more thing, just about dating methods. Like, she's saying that it's not good for predictability of volcanism.
Yeah.
Okay. It doesn't mean that dating methods is unreliable. It is extremely reliable. Yes. It has great precision.
Yes.
And great precision, great accuracy.
Yes.
So
dating is very, very important, and we use it for all kinds of things. However, we do not use it to count down to the next eruption. That's what it's not good for.
Yes. There we go. Summed it up.
Yeah. Thank you for emphasizing.
Yeah. No worries. So I know you wanted to briefly talk about the USGS volcanic alert system. Would you mind elaborating on that? I know you had it in this segment. I just wanted to make sure that you still wanted to cover that.
Yeah, so the volcanic, it's really simple. The USGS volcanic alert system, basically you just like put in your email, and it sends you, the volcano observatories, they write up reports for like literally every like minor change in the volcanic system. And even if nothing has changed at all, they put out weekly reports for every volcano that we monitor. So if you're someone who is worried about things like Yellowstone or eruptions, and you want to be up to date and get it from the actual source, not random news articles that low-key are probably gonna lie to you.
Yeah.
That's what you want to do, is you want to sign up for the USGS volcanic alert system. Even if you don't necessarily live in a volcanic area, but you're interested in it and you think, you know, it's cool, it's fun. You do get a lot of emails. I think you can change the settings for what you get emails for. Like if you live next to St. Helens and you only want St. Helens ones, I'm sure you can like sign up just for those ones. I'm signed up for all of them, obviously. But I think that's something that's really important, is when people, I know that people want to know these things, and I really hate having to come on here and or go on my TikTok and be like, don't look at regular articles, because scientific research articles are not accessible. So I don't want to be telling people that they need to be reading the actual research, because it's not written in a way to be accessible to non-specialists. So I don't want to go on there and tell people not to read those and not provide an alternative. The alternative is USGS. They literally pay people specifically to write things that are accessible to like the modern people. And also everybody's super nice. Like you could probably call them. You could literally call them and be like, hey, can you talk to me about Yellowstone? And they would probably answer. That's the whole point of USGS, is it's not just monitoring, it's also public education. And we're really interested in that. If this is something that someone is worried about, the first thing to do is to sign up for the alerts, and to make sure that you're getting your data from official sources and not from people who have an ulterior motive, like, you know, selling articles or subscriptions or whatever. And then if you have more questions, just call them. Yeah. They'll be very happy to touch you. So, you know, so I think that's the thing, is while it is hard for some things to be accessible, this is not one of the scenarios where the information is inaccessible. Everything I'm talking about is very, very accessible. I know that some people don't know where to look, but that's why I talk about it so much. I'm telling you where to look. Go look on USGS.com. You can even Google USGS Pub Talk, Yellowstone Misinformation, and you will get an hour-long lecture on this information from the scientist in charge of the Yellowstone Volcano Observatory. Problem solved.
Boom. Look at that.
Yeah.
Solved all your problems.
Yeah.
You only had to listen to this or watch this for like an hour and a half.
Yeah.
So speaking of time and duration, do you have any last things that you want to say, any shout outs you want to make before we end the shindig?
I did have a couple of things. And the first thing is that I am starting a YouTube channel. I have not recorded or posted a single thing. However, I made the account. So if people want to follow the account, they can do that. And it's under the same username that I have on Instagram and TikTok, which is Dykanite. And I might do some long form versions of my lessons on TikTok. But the main thing is that I want to interview the scientists who actually do this information. So like like Yellowstone, for example, I would love to interview someone who works at the Yellowstone Volcano Observatory, because I feel like as a science communicator, like I also work full time as a scientist, but I am only an expert. I'm at the beginning of my career. I don't want to call myself an expert on anything, quite frankly, but I only know in detail things that I specifically work on all day, every day. And I can do a great job reading other people's research and deciphering it and making a video about it. But a lot of people want to hear directly from the source. I feel like it's irresponsible to act like you are an authority on something that you're not. So I would rather bring in the person who's the actual authority and do that instead of, I would rather give them a platform to talk about their research than me trying to translate it for them. Because no matter how good you are at geology, you cannot be an expert on every subset of geology. It's just, there's too much information to know. So that would be the first thing. I have no idea when I'll get to making those videos, but the account is on there.
Hey, by the time this comes out, you know,
probably actually.
Yeah, we're good. No worries.
And then the only other things is that I do a lot of LGBTQ plus activism on my account, and I'm going to be doing a presentation on LGBTQ resources in STEM for the launch of a social media app called Adele, which would be very cool. And then I am also raising awareness of a very cool volcano themed queer art collection called Volcanoes, which
Nice.
I know they're going to be starting a Kickstarter for it in February, so it'll be going on for a while, and I'm going to put both of those in my link tree on all of my accounts. So that would be very cool for people to look into also, and you get rainbow themed volcano stuff, which I think is very cool personally.
Dang. Hey, make sure you send me those links. I'll put them in the description.
Yeah, for sure. I will. Thank you.
Yeah, absolutely. Is that it? Is that all you got? You said you had.
Yeah, I think that's all I got.
Well, if that's all you have, this has been a wonderful time. I've learned a lot. I'm sure the people, I guess, whoever's paying attention to this has learned a lot as well. This has been great. You don't get to hear about volcanoes that much unless you're just doing a deep dive on YouTube, watching the wrong videos.
Yeah, watching the misinformation Yellowstone videos.
Yeah.
Don't do that.
I know who you are. That's cool. But again, thank you, Denali. It's been a wonderful time. And it's been awesome getting to meet you and doing this. It's been great. Thanks for being on the podcast.
Great. Thanks so much for having me.
All right. Cheers. That is all for this episode of Everything STEAM. I just wanted to take a quick second and thank Denali for taking the time to share her knowledge and expertise on volcanoes. Definitely make sure you check out her content on TikTok, Instagram, and YouTube. You can find Denali by searching Dykanite. I would also love to mention my amazing team for their collective efforts to make this show happen. This podcast was edited by Ariel Piermont, marketed by Courtney Page, QC by Panyapit Urixit, and our episode art was created by Gabrielle Edmiston. After the episode, please give our podcast a rating and review on whatever platform you get your podcasts on. We're always looking for feedback, and the rating would greatly help us out in the fight against those algorithms. Lastly, be sure to check us out on all the socials for podcast news, upcoming episodes, and just fun STEAM content. Search Everything STEAM on Instagram, TikTok, Facebook, and Reddit to join in on the fun. Once again, thank you for listening to Everything STEAM. I am your host, Sam Stanford, and as always, stay curious.